Okay, this is my fourth and final video for my Algebra 3 Prerequisite chapter number 3, in which we're going to be confronting rational exponents. Up until now, we've been talking about exponential notation as well as radical notation. What I want to do is I want to relate radical notation to rational exponent notation. We can rewrite a radical as a rational exponent. And so we're going to start by considering the following argument. But think about the properties of radicals here. I notice that I've got written 7 to the 1/2 that to the second power. Recall that using a power to a power property, if you took a power to a power, you'd multiply the exponents. So with an expression like this, if I took 7 to the 1/2 times 2, well, anything times its reciprocal is 1. So I just get 7. Another way to look at this is I'm taking a number and squaring it, and I just get 7. So what this means is, what number did I square to get just 7? Well, there's one number I can think of that when I square it, I get just 7. It's the square root of 7. So what this really means is we can draw the conclusion that if I were to take 7 to the 1/2 power and square it, that 7 to the 1/2 is really tantamount or equivalent to writing the square root of 7, okay? So generalizing this, we could say that 7 to the 1/2 is the same thing as the square root of 7, where I'm going to write a little 2 out here. But we say, consider the following definition. When we talk about radical notation, we're really usually writing the nth root of a as this. We say the nth root of a. But using this definition, we're saying that that's the same thing as a to the 1 over n power. So if I wanted to take a square root, we could take something and raise it to the 1/2 power. If I wanted to take a cube root, I could raise it to the 1 over 3 power. If I take a fourth root, 1 over 4 power. So furthermore, you'll notice I also listed this here, but if we said a to the negative 1 over n, this is just using our negative exponent rule. It says if you have a negative exponent, we can actually just move it downstairs, move the base downstairs, and it becomes a to the 1 over n in the basement, which is 1 over the nth root of a, where a is not 0. So really quickly, let's take a look at evaluating these 5 expressions right here. But you'll notice that all of the numerators of their rational exponents are 1. So we're going to deal with other than that situations next. But for right now, when I say 25 to the 1/2 power, remember that that means the same thing as the square root of 25, which is just 5. We could just actually just say, looking at this, I get 5. Okay. Same thing over here, where I say, well, I recognize that this is the cube root of 8. 8 to the 1/3 is the cube root of 8. But I could also say, well, what is the cube root of 8? What could I take times itself 3 times to get 8? It's just 2. Looking at this one here, now this is kind of important. I want to point out that this is really the same thing as saying this. The thing that is being raised to the power really is truly only the 81 here to the 1/4. So what we're going to do first is our exponent, which is the fourth root of 81. We say, well, what can I take times itself 4 times to get 81? And that's actually a perfect fourth of 3. So we say this is negative 1 times 3 here, which we get negative 3. So negative 81 to the 1/4 is actually negative 3. Whereas if I were to say now, include this negative here to the 1/3, we say, what could I take times itself 3 times, or what's the cube root of negative 8? We'd say, well, negative 2 times itself 3 times would give us a negative 8. And then last but not least, we say, what's the 27 to the 1/3 power negative, or negative 1/3 power? I want you to recognize that this is still a cube root of 27. It's just that using our rules of exponents, remember that we have to take this negative exponent and move it downstairs. So we get 1 over 27 to the positive 1.
I need computers. So many people in here.
So we have 1 over, and the 27 is a perfect cube of 3. So we get 1 over 3. Okay. So now, building on this, we say all those examples had 1 in the exponent. Let's consider this, a to the 2/3. That would be the same thing as a to the 1/3 to the 2, recalling that you would multiply these two things, and you would get 2/3. So what would be true about a to the 2/3? Well, if it's a to the 1/3 to the second, that's the same thing as the cube root of a squared. Another way to look at this is a to the 2/3 is the same thing as a squared to the 1/3. So in either instance, we're saying that we're taking the cube root of a squared thing, or a squared a. And the conclusion we can really draw here is that if we were to take a to the 2/3 and rewrite this as the cube root of a squared, or the cube root of a squared, you'll notice that this top number in our exponent here is considered to be the power. And the bottom number in this exponent here is going to be our index. Okay, so looking at this definition that we have here, expanding it, we basically say that the nth root of a represents a real number, and m over n is a positive rational number, where n, say, is greater than or equal to 2. Then a to the m over n is really this, where the top number here, the top number, is going to represent the power, okay, on our radical expression, and the bottom number here is going to represent the index on our expression. So when you see things such as these here that say 27 to the 4/3, really we could rewrite this as this. We say 27 was our base, and we're taking it to the 4th power, and we're taking the cube root of that. Okay. Whereas, you look at this, you say 4 to the 3/2. It's really 4 cubed square root of that. And then also this here, we could say, well, we're going to have to adjust this around because of the negative exponent, but it is the 5th root of 32 to the 2nd power. So let's go ahead and evaluate these. And one thing that I do want to mention is this: in terms of evaluation with rational exponents, it is always easier to do the root first and then take things to the power, instead of taking them to the power, making them bigger, and then trying to do the root, the nth root here. So when I look at 27 to the 4/3 power, the first thing I'm inclined to do is take the cube root of 27, which I know 27 is a perfect cube of 3. So to rewrite this, now I'm going to say, well, this is the same thing now as 3 to the 4/1. I already did the cube root. So 3 to the 4th power is 81, and you'll notice that when you took 27 to the 4/3, 4/3 was improper. That is a little bit bigger than 1. So what do you naturally think is going to happen to a number when you take it to a power that's a little bit bigger than 1? Well, anything to the power of 1 would stay the same. So anything to the power greater than 1 is going to inflate a little bit here. So let's take a look at these last two. We say 4 to the 3/2 power. That's going to be the square root of 4 cubed. Really, that's what we're doing here. So let's go ahead and start with the the denominator here, which would be the root. So we say the square root of 4 is 2, and now I'm taking 2 to the 3rd power. I just need to cube that, and I get 8. And then for this last example here, using our properties of exponents, the negative exponent rule says that we're going to take this base and we're going to move it downstairs to the denominator. So now this is 32 to the positive 2/5. We're going to treat this the exact same way. We're going to start by taking the 5th root of 32. The 5th root of 32, what could you take times itself 5 times and get 32? Is 2, and then we say square the 2, you get 4. Okay. So now, last but not least, we're going to simplify these expressions down here in which we have rational exponents already. So using our rules of exponents, we have 2 times 5. We're going to start with our coefficients here. Our product rule says we'll start with the coefficients. We get 2 times 5 is 10. And then if I were to take x to the 4/3 times x to the 8/3, I would get x to the 4/3 plus 8/3, which gives us 10x to the, this would be just adding straight across, it'd be 12/3. And we can actually reduce that even. We say 10x to the 4. So that would be our simplified expression, whereas now using our quotient rule, again, we'll start with our coefficients here. 20 divided by 5 is going to be 4. And if we were to take x to the 4 over x to the 3/2, we're going to get x to the 4/1 minus 3/2. And in this case, we're going to need a common denominator here. Remember that common denominator here in this case would be 2. So we'd really get 8/2 minus 3/2, which is going to be 5/2. So we get 4x to the 5/2, and we could even rewrite this as 4 times x to the 5th power, taking the square root of that right there. I like this the best. So the last thing I want to kind of indicate is that sometimes it's easier to reduce an index, and the way we're going to do this is really we'll just rewrite this as a rational exponent first. So x cubed, the 6th root of that is going to be x to the 3/6 power. You'll notice that this collapses to x to the 1/2, which is really just the square root of x. So these two would be equivalent statements.